Ladies and gentlemen, colleagues and friends, it's a pleasure and an honor to be giving this lunchtime lecture. What I would like to do today is talk in a broad sense about nanomaterials and their thermodynamics, and really bridge the two areas that I have always been working in, or perhaps the three areas I've always been working in: geochemistry, solid-state chemistry, and material science. And there really are very few boundaries between those fields. It depends a little bit on what the materials you work on are and whose meetings you go to, and you go to all of them really. So the points I'm going to make today really center about the thermodynamics of materials at the nanoscale. Perhaps the two main points are that nanomaterials, and particularly nanoparticles, are everywhere. They exist in the environment. They have existed through geologic time. They probably account for much of the chemical reactivity in the Earth and other planets, and perhaps arguably in interstellar space as well. We have discovered them and given them names and made them fashionable, and of course made them useful technologically. But really, the main question about nanomaterials is how are they different from bulk materials? What we know certainly is that they're more reactive, but the point that I'm going to try to hammer home today, is that they're also different in their fundamental thermodynamic properties, and that many of the things that we have been ascribing to kinetics are in fact thermodynamically driven. So perhaps a subsidiary point I want to make today is that when you don't understand something in archaeology, you say something has ceremonial purposes. And when you don't understand something in chemistry and material science, you say it's kinetically controlled. In fact, all of those may be true, but there are often underlying other things, in particular the thermodynamics. So let me illustrate with some examples and the breadth of the subject, and then I will go through and give a few specific examples. So, if we think about current issues, energy, environment, waste, climate, these are interrelated. They are all essentially the physics and chemistry of Earth materials. Earth materials in the solid state, all the way from the core to the mantle to the crust to soils to particulates in the atmosphere. Materials in the liquid state, the Earth's liquid outer core, metallic in nature, the oceans, magmas, lavas, etc., rain, which thank heavens we had some last night. They are also important then in the balance of energy in the planet, in the balance of materials in what we call geochemical cycles. They are important then in how we interact with the planet, and certainly the human population being at the level it's at now and using resources the way we use them and emitting CO2 into the atmosphere the way we currently do it, certainly has global impacts, and to understand those impacts, to understand even the persistence of CO2 in the atmosphere, one has to understand geochemical cycles, and indeed one has to understand nanomaterials. For example, the precipitation of carbonates in the ocean and elsewhere may very well occur through nanophase intermediates. So, what do we know? We know that processes, the rates of processes, are controlled by kinetics. We know that the end products are eventually controlled by thermodynamics. Another slide I sometimes show, but I don't have it here, is you're standing on top of a ski hill at sunset time. The ski lodge is down below you, it's getting dark, and the caption would read, if you don't know which way is downhill, you're not going to make it back for cocktails. Similarly then, energetically, with nanomaterials, as well as with other materials, as well with all processes, whether they're technological or natural, if you don't know which way is downhill in free energy, you have a hard time making things happen. So, what about the major issues then? In many cases, be it sol-gel synthesis, hydrothermal synthesis in the natural environment, air particulates, etc., one makes particles, or nature makes particles, or technology makes particles, and those are typically initially made as small particles. And those small particles often persist simply because coarsening requires higher temperature, and in fact requires very often stripping off the hydration layers, the hydration shells on particles, to enable them to come together. So therefore one is left with materials which are metastable with respect to beautiful bulk single crystals, yes, but which are very persistent. And dealing with the chemistry of metastable states is nothing new. A mixture of hydrogen and oxygen has well-defined thermodynamic properties, but at the same time you should not light a match to it if it's within the combustible range. Similarly, we ourselves are metastable, metastable with respect to CO2 and water and pile of ash, but it does not matter for the most of our lives. So dealing with metastable states is really something that we do all the time. Dealing with constraints, saying let us deal with this system but not enable it, not allow it, if you will, in this particular case to coarsen, then we have an issue basically of what happens at the nanoscale. So nanoparticles, of course, have surfaces. Nanoceramics have interfaces. I won't talk too much about interface energies. My colleague Ricardo Castro at Davis has been working a lot on those issues, but the basic issues are the same. You have surfaces, interfaces between a particle and water, interfaces between a particle and air, interfaces between particle and particle. And if those areas, if you will, are defined by the initial synthesis, then you have to say, how does the system optimize its free energy? And the major issue then is that different crystal structures have different surface energies. So different polymorphs have different surface energies. Hydrated and dehydrated materials have different surface energies. Of course, different crystal faces have different surface energies. And here we really have a fortunate confluence of a number of things, of theoretical calculations that more and more are able to deal with nanoparticles and surfaces and systems of the right size, that one begins to see the complexity. One has spectroscopic transmission electron microscopy, many other techniques that are better and better able to look at things at the nanoscale. And we have thermodynamic measurements in which we now can measure the surface energies of these materials, and we try to bring all of these things together. So these are the major issues. How does thermodynamics change at the nanoscale because of the surface energies, the different surface energies of different possible configurations of the system we deal with? So, question about magnitudes. You say, what does it matter? Well, let's say that we have typical surface energies of materials that are on the order of a couple joules per meter square. That's a normal surface energy of a material. You see that from DFT calculations, you see that from measurements. Perhaps one will have a surface energy of 1 joule per meter squared, one of 3 joules per meter squared. The difference is 2, or the difference is 1 or 1.5. And you say, well, you have a typical surface area of 100, couple hundred meters squared per gram. You say, that's a couple hundred joules for the sample. But when you look at thermodynamic calculations, your thermodynamic calculations are per mole. And a typical molecular weight, say, for iron oxide is 150. Then when you plug in the data, you realize that in terms of energy per mole, the surface area per mole is huge. The energy gain, that is the energy, positive energy, is huge. And then you begin to get energies that are on the order of chemical energies. If you think of a chemical equilibrium, changing that chemical equilibrium by a few kilojoules per mole will shift that equilibrium tremendously. And that's what I'm going to be talking about for the rest of this lecture. So if we take a look then at some of these issues, we can do various calorimetric measurements of surface energies. And in principle then, if you make materials and they have a different surface area, and you somehow measure their enthalpy of dissolution, for example, as a function of surface energy, that difference should give you, as a function of surface area, that difference should give you a surface energy. The difficulty is that, of course, particles have very active surfaces, and those surfaces are never naked. They are always covered. They're always dressed up, whether they're dressed up with the molecules you intentionally put there to stabilize a synthetic nanoparticle with an organic coating, whether they have grabbed that from the atmosphere, whether they have water, CO2, or something else. One has to realize that those particles, in fact, create a chemical system which is complex. In fact, perhaps it's better to think of nanoparticles and what's on their surfaces as a single large molecule. People who look at things like nanoscale effects and optical properties realize that the coating you put on a nanoparticle will shift the spectrum. Therefore, again, the nanoparticle, in a sense, is a giant molecule. And in a sense, it's no bigger than protein molecules. We know how to deal with those. So dealing with them, then, one has to deal with what's on their surfaces as well as the molecules. So what we do is we do a combination of calorimetric measurements. We measure the energetics of the particles by dissolving them in a molten salt solvent, and then we measure the hydration energies if the particles have water on them. We need to measure as well, basically, the exact amount of water, and there have been embarrassments in the literature where people have come to wrong conclusions because they did not realize that particles have a lot of water on them. And I will remind you that water, H2O, has a low molecular weight, 18. Iron oxide, I said, as Fe2O3 has a molecular weight of 150. So a little bit of water goes a long way in terms of molecules, in terms of lattice vibrations, in terms of coating things. You can say, oh, you have 1% water, that's no big deal, but your 1 weight percent water can turn out to be 10 mole percent water on your material, and it can turn out to be enough water to coat the surfaces completely. So those are things you need to think about. You always have to think about the total chemistry of your system. So first thing I want to talk about is control of polymorphism at the nanoscale. We know a number of oxides. I'll be talking mostly about oxides today. We know that a number of oxides are polymorphic. TiO2 has rutile, anatase, and brookite. Al2O3 has alpha and gamma alumina. The iron oxides and the manganese oxides seem to have a plethora of structures possible. We have found also that very often the structures that are metastable as bulk phases, gamma alumina relative to alpha, gamma Fe2O3 maghemite relative to hematite, anatase relative to rutile, that all of these at the nanoscale seem to persist, and our argument is that they persist for thermodynamic reasons, namely the polymorph that is metastable at the bulk scale often has a lower surface energy, and therefore at the nanoscale there will be some sort of crossover in the energetics. Alumina is an example then. This was the work that we started, oh my goodness, in the mid-1990s, and we realized that to understand alpha versus gamma alumina, we had to understand not just the polymorphism, but the hydration energies as well. And here then we show the crossovers. On the left we show the energy and I use energy and enthalpy and even free energy of surfaces as virtually interchangeable. For most of the materials, the surface entropy is actually small, and we have some evidence for that for a number of systems. We see then that as one increases the surface area of a material, one makes the material more metastable. But if one increases the surface area of a material that is initially metastable by a smaller amount for a given surface energy, that is, for a given surface area, that is, with a lower slope of the roughly straight line relating enthalpy and surface area, there can in fact be a crossover. Or if we look on the right as a function of particle size, of course if the energy goes with surface area, particle size and surface area are not linearly related, so one gets a different shape of a curve, and you say, well, when is the material really nano? If it has a small surface energy, like gamma alumina, you really need more surface area before you notice that the properties are different. So the term nano itself is relative. It's for what property, it's for what surface energy, it's for what function. It's for X-ray line broadening on the one hand, it's for crossovers in stability on another. There's no absolute, you say this is nano, that is not nano. You have a particle size distribution. So to me, something becomes nano when something you're interested in becomes significantly different. Okay. If we then take a look again at other materials, for example, if we take a look at other iron oxides, for example, what we find is that there are a large number of iron oxide and iron oxyhydroxide polymorphs. If we look at the upper curve, at the upper diagram, because these things always are hydrated, so correcting for the water adsorption enthalpy to anhydrous materials is probably not the real world, except perhaps maybe in space. What we see is that for large particles, one has a significant difference in the enthalpy and also in the free energy between polymorphs. But for small particles, because the ones that are metastable in the bulk have lower surface energies, they all become competitive. So it is no wonder in the iron oxides then that one often, in both synthetic and natural environments, gets a mixture of materials. And of course, each of these phases will have somewhat different properties, different magnetic properties, different optical properties, different transport properties. So if you're trying to maximize the properties of a thin film, for example, of an iron oxide, you have to control what phase you have, and that control can be quite different at the nanoscale than it is at the bulk scale. And indeed, some of the first work that we did on the iron oxides came with samples from a company. And what that company said is, we will give you wonderful samples, but we don't want to be identified, because if people know something that these are our samples, they might discover some of our secrets. So we had wonderful samples we were free to characterize and publish, but the source of the samples remains unknown to this day, and this was work we did 15 years ago. So there are certainly practical aspects to this, and I remind you, of course, that most of the TiO2 that's used in catalytic and solar cell work, etc., is anatase rather than rutile. I remind you that most of the aluminates used as supports and catalysts and so forth is gamma alumina and not corundum. Okay. There are other reactions, dehydration reactions. It turns out that the oxyhydroxide polymorphs, things like boehmite for Al2O3, things like goethite for Fe2O3, that is the iron oxyhydroxides, AlOOH and FeOOH, they sort of have a picket post of structure of hydroxyl groups decorating their layers, and they seem to have rather small surface energies. So if one calculates the dehydration reaction at the bulk scale and at the nanoscale as a function of water fugacity, one gets a typical sigmoid curve, but that curve can be shifted by as much as 100 degrees centigrade, favoring the hydrated polymorph. This is important geochemically because there are environments in which hydrated iron oxides, hydrated aluminum hydroxides exist. Geology tells you that's a higher temperature environment. You should have corundum or hematite. There are ornate explanations as to why you don't, but in fact the reason you don't is the temperatures are still low enough, you don't coarsen the particles, and the hydrated phase is still thermodynamically stable. Same sort of thing holds then if you're making materials for technological applications. They will dehydrate and coarsen often simultaneously. That is, once the temperature is high enough to get rid of the water, then the particles can also come together and coarsen. Oxidation state effects. Similarly, if one has materials that have different surface energies for different oxidation states, then in fact particle size, small particle size, will favor that material that has the lowest surface energy. And oxidation reduction equilibria will shift as a function of particle size. That is, if one plots a standard Ellingham diagram sort of thing, oxygen fugacity versus temperature, those lines will shift substantially by several orders of magnitude in FO2 at the nanoscale. This is important because catalysts are nanoscale, because many of the materials that one uses now or is developing now for fuel cells and batteries and so forth are nanoscale. If one looks at the redox reactions, well, they're not the same. They're thermodynamically not the same. And indeed, it is quite possible that the control of redox reactions in biological cases, the particle size may actually be selected for to properly match other enzymatic pathways, and similarly perhaps this control of redox at the nanoscale might have had a lot to do with the development of the sort of prebiotic organic chemistry that eventually led to enzymes and to what we're very familiar with transition metals, even things like the manganese cluster that relates to photosystem B. Okay. Some surface energy systematics that we found. I've come into this, of course, having worked for many years in the systematics of thermodynamics of properly crystalline materials and glasses, and I'm convinced then that there is a lot of systematics related simply to chemical bonding in the thermodynamics of materials. I realized that one should be able to see some systematics as well in the surface energies. And one of the interesting things that we've seen is that the surface energy does seem to be related perhaps more to the structure of the material than to the composition. And one of the findings that has held over the last 7-8 years is that almost all spinel structures have rather low surface energies, meaning surface energies at or below 1 joule per meter square, whereas other structures, for example, the olivine structure, have surface energies that are 3-4 times that much. It appears, but this is still a little shaky, that structures that are of significantly lower symmetry typically have higher surface energies. It appears that structures that are hydrated have lower surface energies, and it may appear that structures that have mixed valence have lower surface energies. Those are trends that we see. Those are still things that need further exploration. So, having said that, let's take a look at some of our examples. Our first example is the cobalt-oxygen phase diagram, because this is where we first realized the redox makes a difference. And that is that if we take a look at cobalt metal, cobalt monoxide, COO, the rock salt oxide, CO304 spinel, what we find is that the rock salt oxide actually has a higher surface energy than either the metal or the spinel, and therefore at the nanoscale, the spinel exists to lower oxygen fugacity, and the metal exists to higher oxygen fugacity than for bulk materials. That is, the phase field of the rock salt oxide is squeezed to be much narrower. There are applications for this. For example, transition metal oxides like cobalt oxides are used in catalysis. For example, they're used as catalysts for the oxidation of carbon monoxide to carbon dioxide. It was assumed that if you put in COO under those cobalt oxide under those conditions, the oxygen fugacity would be such that it would be the rock salt oxide. But because of the enhanced stability of the spinel, the nanoscale, it is in fact the spinel, and it is in fact the mixed valence CO2 plus CO3 plus oxide that exists under those conditions, and that may have a lot to do with the mechanism, and one needs to look at that then perhaps in more detail. Similarly, if you look at the reduction of oxides in the electron microscope, the redox equilibrium may shift, and what happens under the electron beam and what happens at the low FO2 that you're looking at in a high vacuum, you have to worry that your nanoparticles will be reduced differently from your bulk particles, and differently not just because of kinetics, but because of thermodynamics. The iron oxides are even more extreme, because the monoxide, or nominally monoxide wustite, in fact, does not exist at low temperature. It peters out at low temperature even in the bulk. And in the nanoscale, because the spinel magnetite is stabilized, the Wüstide field essentially disappears. And indeed, I believe nobody succeeded in making FeO nanoparticles. They always come out magnetite, because in fact the Wüstide field would start existing only about above 1,000 Kelvin from the calculations, at which point that temperature is high enough to dehydrate and coarsen the particles. So basically the nanoparticles simply cannot be made. Manganese oxides, same story. In this particular case, Mn3O4, the spinel, has the lowest surface energy, Mn2O3, the Bixbyite structure, intermediate, and MnO2, pyrolusite, the highest, and therefore again the phase diagram changes, and because these have different hydration energies, the phase diagram changes as well, whether the surfaces are hydrated or dehydrated. And one of the things that a student of mine, Nancy Bergner, found is that hydration can actually induce the reduction of Mn2O3 to Mn3O4 under the appropriate conditions. And again, this is thermodynamically driven. So what does this mean? For example, if we want to use manganese oxides as an indicator of their formation conditions, as an indicator of the oxidation level in a soil, well, maybe they don't tell us about what happened when these things formed 10,000 or 1 million years ago. Maybe they told us we had rain yesterday, because the hydration and the oxidation state are closely balanced, and those reactions seem to occur fairly rapidly. Okay, let's then think about other applications. I've talked about most of these, catalysis, etc. One of the examples then has to do with looking for materials that are potentially good catalysts. And here I would like to make a related point. I would like to come up with another example. Here we basically think about some of these materials essentially in terms of the calcium manganese oxide, materials that have been made sort of as biomimetic materials, thinking of the photosystem 2 calcium manganese clusters in photosynthesis. And indeed, a colleague of ours then has made a number of these oxides, and we decided that we wanted to look at their thermodynamics. Now, these are layered oxides related to the bernesites that occur as well in other alkali and alkaline earth manganese oxides. The role of the calcium or sodium or potassium is charge balance in the materials. Instead of forming the parent Mn2O3 structure or the parent MnO2 structure, one forms materials with mixed valence and with layers, and with essentially a layered structure. What we found in terms of the energetics of these, I think I have them, well, let me go back actually, don't have that on here. What we found is very interesting. First of all, the energy of oxidation reduction in these materials is smaller than that of the Mn2O3 MnO2 equilibrium. That is, one can form mixed valence thermodynamically more easily. Secondly, the materials are layered structures so that they're genuinely nanoscale, and therefore diffusion is not a problem. Thirdly, the materials are hydrated. Now let's imagine some sort of reaction in which one wants to transfer electrons and or transfer ions through the interface. The interface, let's say, between the oxide and water. In order to have that sort of transfer, if the water on that interface or that surface is held really tightly, then it's difficult to move some other ion, a lithium and lithium ion battery, manganese ion in and out of solution, etc., because it has to displace a tightly bound water. Therefore, one of the things that, in addition, makes these materials good catalysts is having relatively loosely bound water. What we found is there's a very good correlation between surface energy and the binding energy for water. That is, the higher the surface energy, the more tightly the water binds to the surface to essentially relax the surface. So, another criterion for excellent function for these materials, in addition to intermediate redox states, lower energy of oxidation reduction, a layered structure, easy accessibility, is a low surface energy, a surface energy that then enables one to easily move ions and molecules in and out. So that's beginning to be a prescription. Look for a good material. These are the properties you need to have. We've looked for similar things with the other layered manganese oxides. This is just variations on the same theme. The bernesite structures, and indeed several of the other related structures, show similar trends, and perhaps then we begin to understand why these layered oxides are really very, very active in both a thermodynamic and a kinetic sense. Battery materials. Of course, one is interested in things like the lithium cobalt oxides, the layered rock salt structures that then are right now the commercial materials, although they do have their problems. What we found, initially surprisingly perhaps, but I think it makes a good deal of sense. Here's just an example of what they look like, basically. So we have a parent rock salt structure, but we have layers of the lithium, layers of the cobalt, and of course, as one lithiates or delithiates, one reduces or oxidizes the cobalt, and that is your method of energy storage. But of course, to get those electrons in, to get those lithiums in and out, one needs to have transfer through the surfaces, through the interfaces. And this again is then where the oxidation reduction energy and the surface energy play a role. And what we found, oops, did I miss one here? Yes. What we found basically, and this was rather interesting, we found that the surface energy of these materials is really quite low. Lower than the parent rock salt oxide. These layered materials are really more like the oxyhydroxides. At the same time as we were doing this work, Shirley Mung's group at UC San Diego was doing some studies on them and some calculations as well. And we did not know, until I happened to give a seminar down there about 2 years ago, that we were basically coming to absolutely similar conclusions. That basically these materials had low surface energies, low hydration energies, and that a good part of their function then probably related to the easy transfer through an interface. Well, let's take a look at some other material that is a touted battery material, one that does not contain cobalt but that contains iron, namely the lithium iron phosphate olivine structures, which again have been commercialized, but they have somewhat high resistances and they seem to have not very easy ion and electron transfer. Well, we have not measured, we're in the process of trying to do so, the surface energy, but we have measured the surface energy of other olivine structures, and they're sufficiently higher than those of spinels that we hypothesized that one of the limitations of this family of materials is simply the high surface energy and the high energy of binding of water on the surface. So the general principle then, the general idea, perhaps the building, if you will, the recipe for building a good material, obviously it has to be nanoscale so that you don't have long diffusion paths. Obviously, it has to have the right redox characteristics, and those are affected by the particle size. But it also should ideally have a low surface energy and therefore, or correlated with that, a low hydration energy, so that whatever molecule you're sensing, transferring, functioning with does not have to battle against extremely tightly bound water in order to get its day at the surface or diffusing into the bulk. So this is effectively then some suggestions as to what families of materials or what characteristics of materials one might look for to have good functional materials, be they catalysts, be they battery materials, etc. So, implications in general then, implications I think for nanomaterials in the environment, implications then that the materials that are most functional biologically march to the same drummer, implications then that the materials that one makes that one synthesizes should, again, one needs to pay attention to the surface energies and the hydration energies and the polymorphism, and therefore one basically needs to think about how one does this. Well, the path forward then might be to look in detail at specific systems or to look more generally, to look basically whether we can get a systematics of surface energies, put some of this into CalFad type calculations. Right now, if we think of phase equilibrium calculations, both first principles calculations by DFT and then phase equilibrium optimizations by the various CalFad type methods, the two things that are not included in those very much at present are high pressure, which the geophysics community needs because of the interior of the Earth, and the effective size. And if we have these surface energies, we should then be able to say, okay, let's then say we have coarse particles, we have intermediate sized particles, we have very fine particles. Let us build a database, let us see which reactions are really shifted, and then basically compare them and use them in applications. So, to conclude then, and this is the Alexis calorimeter that is in our laboratory, so simple that even my Labrador can learn to use it, and believe that these calorimetric data that we have gotten for nanophase oxides has not only let us understand the thermodynamics, but use the thermodynamics to understand function and perhaps to even predict the properties of new materials or the properties of old materials through geologic history. Thank you for your attention.
Did we have any questions?
Thank you, Alex, for that sort of 15-year retrospective. It's great to see it all packaged together. And thank you for reminding us that when we put a nanoparticle in ultra-high vacuum or even high vacuum, we're looking at the carapace of a once vibrant living insect. Have you thought to think about taking a step beyond understanding just the nanoparticle, as complex as that is? Because when we're using it in batteries or in the geophysical or in the environment, it's often in contact with another surface. So how do we then start to pry apart how those surface energetics are then influenced by the surfaces they are in contact with?
Indeed. A simple conceptual case is, of course, a dense nanoceramic in which one still has nanoparticles, but rather than being in contact with water or air, they're in contact with each other. Mm-hmm. And then one can play the same game of measuring interfacial energies. And indeed, I did not talk about that here. In general, the interfacial energies are smaller than the energy between particle and particle seems to be on the order of about half of that between particle and air or particle and vacuum. Indeed, we have been measuring some of those. Our colleague Ricardo Castro has been as well. There are, of course, calculations of those. The difficulty is that there are many interfaces. So then, of course, you have to think about which crystal faces. Do you have a really tight contact? Do you have a grain boundary? Do you have some sort of crystallographically coherent boundary? Or do you have what I call sort of a loose contact where you've got two surfaces, but they still have an entrapped water layer of a few molecules or an entrapped solvent layer of a few molecules? And real materials then will contain a mixture of all of these different things. And therefore, what simplifications you need to make to say this is the most important thing really depends on the system you have. But yes, that obviously, what should I say, is going to keep people busy for quite a few more years. And I might say that the whole idea of surface complexions or interfacial complexions, for lack of a better name for them, really has to do with all of these same things. And I might finally say that when you have multi-component systems, as you get things into the grain boundaries, the whole energy of the system may actually be more favorable rather than less favorable, because you can then have some sort of intergranular films, and that may actually be the lowest free energy of the system once you have relaxed the condition. Remember, the definition of the term surface energy, rigorously, is the change in the energy of the material, the change in surface area, nothing else changing. If in fact you're in a multi-component system, everything else changes, and you have relaxed those constraints, and you may in fact then have a stabilization of the whole system, by keeping stuff in the grain boundaries and keeping the grain boundaries there because there isn't a better place for the other stuff to go.
So think of it as a standard state. All right.
Pardon?
Think of the grain boundary perhaps as a place where it could create a standard state.
Yeah, exactly.
Thank you, Professor Navrotsky. I'm quite new to this area, so I just want to ask, how do you define the surface energy? Is it just you using the contact angle to melt the certain material?
No. In this particular case, and I purposely did not go into the methodology, but we measure it calorimetrically. The simple measurement is to say, the ideal measurement is you make materials of different surface energies and you dissolve them to the same final state. You can think of it as dissolving it in water. These are ceramics, so we dissolve them in a high temperature oxide melt, and then we get the energy as a function of surface area. Now, strictly speaking, of course, that may involve more than just the surface layer. It may involve some reorganization going into the particle. So it is an operational surface energy. It is not something where you have an idealized planar surface and that's the only thing that's going on. But these data that I've shown you are all based on calorimetric measurements of the change in the enthalpy of the system as a function of increasing surface area.
Okay, thank you.
Very nice talk. Very nice talk. I was wondering if you could give us an insight why spinel oxide surface of lower energy.
You know, it's a hard question to answer. I mean, one does, for example, DFT calculations, and one gets similar answers. But the problem is that does not give sort of a chemist's insight. It's not simply a matter of symmetry, although somehow one thinks that the symmetry of the spinel structure has something to do with it. But then again, the rock salt structure, simple rock salt structure oxides, have rather high surface energies. It's not simply a matter of density of atoms at the surface, because I can give you some examples where a denser material has a lower surface energy or a higher surface energy. So the answer right now is I have no insight into that. I can hand wave a little bit, but you know, the data are consistent, they're consistent with calculations, but to come back and give a Linus Pauling-like explanation of, oh yes, it has to do with this or that, I do not know.
Thank you.
So thank you very much for that. I was interested when you were predicting stabilities based on size, say 10 nanometers as a reference case.
Yeah.
Practical materials are often formed under cases where you have kinetically limited growth, and you get things ranging from cubes to octahedra and platelets. So what are we to take away from sort of predictions of stability based on lack of knowledge, really, what we mean by the shape of the nanoparticle?
So we have some data, for example, for zinc oxide and also for TiO2, where we have nanoparticles that are essentially equant in shape and nanoparticles that are, you know, much more acicular, much more nanoneedles, or nanorods, or nanowires, if you will, and also that are nanoneedles. And therefore, a similar surface area, we see that the equant particles have the lowest surface energy, the rods higher, and the needle tapered materials the highest. The excuse or the cop-out that I make here is that what we measure are real nanoparticles. So the real material that one is likely to make, which has a distribution of particle sizes and of particle shapes, that is the material that we're actually measuring, so that number may be useful. But to tease out of that the energy of different surfaces and different perfect surfaces, where in fact these are probably quite imperfect in terms of surface defects, in terms of corners, in terms of pits, etc., that I think from experimental measurements of this sort is difficult to do. So in a sense, what we're dealing with are the real world materials which have all of these complexities that are difficult to separate out.
have any other questions? Let's thank the speaker again.
Thank you.